So the last part of the discussion about volatile variables, we'll just discuss some of the usage considerations to keep in mind when you use them in your programs, like for assignment 2B. You should be very careful how you use volatile variables. You can use them for things like the flags that we've looked at to ensure that the code will stop properly. This thread will stop properly when another thread sets the mDone flag to true. That works, and volatile will help make sure that happens. But if you're not careful, you can end up with busy waiting and spin locks. So that could be a problem. This concept of busy waiting is probably something that should be handled by higher level abstractions, concurrency libraries. So for example, if you take a look at the atomic long class that's part of the Java atomics package, you'll see that it encapsulates volatile and shields you from the details of how it actually works. And that's nice because you can just use these methods like get and increment or decrement and get and so on and not have to think too much about it. So Doug Lee has a nice video that talks about building concurrent library abstractions and how you can build layers of software that shield you from these low-level niggling details that otherwise are confusing and hard to reason about. And you can take a look at this link for more information about that. If you have complicated operations that perform multiple instructions or multiple steps, then volatile by itself is typically not sufficient. So a good example would be where we're going to have some counter, which is volatile, and then we do these increment operations in different threads. And the problem is that something as simple as counter plus plus, which looks atomic at the source code level, actually ends up doing multiple things. So it ends up essentially doing multiple steps. So when you do counter plus plus, that loads the counter into the register, increments the register by 1, and then stores the register back into the counter. And those things can go ahead and interleave, and therefore you'll end up with inconsistent results. And this is demonstrated by this little table that shows some example of how this might occur, because you essentially have these write conflicts where you're doing these operations and it's not clear whether you get 1, whether you get 2, and that's because we're interleaving the operations and it's confusing. So that leads to what's called a write-write conflict. So the way to get around this, as I mentioned before, is simply to use an atomic long or an atomic integer or whatever you need to use that's atomic, whatever your type is. Then you can use get and increment, and that will do all those steps atomically by using compare and swap or compare and set under the hood. And you can find out more about atomic variables if you read the information here. Now here's another interesting thing that's often very confusing. So if you define a reference, if you have like an object or an array, and you make that volatile, it only makes the reference volatile. It doesn't actually make the object volatile. And this is actually kind of silly in a way, because making the reference volatile is pointless because references are already atomic. So here's an example where we would have the vector class, and as you can see here, the vector class is going to have a bunch of fields in it, and in this particular case, we're saved because vector is synchronized, but the point is that defining vector v to be volatile by itself doesn't make the operations here guaranteed to be accessed atomically. And so element count and element data are non-volatile fields, and making vector v volatile doesn't help you because that only makes the reference volatile, which is redundant because references are already atomic in terms of reading and writing, but it doesn't make the state of the object volatile. So therefore, in the case of vector, they define various methods like get and set to be synchronized. And then that ensures that things will be properly protected internally from race conditions and concurrent access that would lead to corruption. So you use mutual exclusion mechanisms to provide that level of thread safety. We will talk later in the course about other interesting ways of being able to ensure object consistency that are more powerful and more complicated than just using the synchronized keyword. The synchronized keyword is an easy way to do it, but there are other ways to do it as well that are quite interesting. So we'll talk more about this in the context of Java monitor object. We'll also cover this more when we talk later about the object consistency techniques and the happens before relationships and so on. As we discussed earlier, the semantics of volatile are not the same as they are in C++ and Java. And this is very confusing to C and C++ developers. So in C and C++, the basic intent of volatile is to say, this variable may change in unexpected ways, so don't optimize it, compiler. Don't optimize it away. Even if it appears redundant, don't get rid of it. And so if you read this link, you can read about the different uses of volatile in Java versus C and C++. In particular, volatile in C and C++ doesn't make something atomic, and it doesn't create what's called a happens before relationship. And we'll talk more about happens before relationships later. You can read about that here. They just disable compiler optimizations. Okay, so that's the end of the usage considerations discussion of volatile. So at this point, you should be well armed to finish up all parts of assignment 2B. And when you watch the video, I give you a few little hints. But make sure you understand what volatile means, because you'll need to use it in the context of that assignment.